3 equal in a random environment? I got a 0 variance estimation. Is n equals 3 enough? Obviously it's not. So this is preventing that, right? This is a term that decreases the n pretty fast, but when n is small enough, it provides some kind of control. So you don't really stop after small n. I mean, another way to look at this is that, what if we don't have this an, but we start with n greater than 100 or something? You could also say, I'm going to stop after n is at least as big as 100. You could also do that, right? So this an is some kind of control. In case, some weird, random, probably unlikely though, but this is random, so you never know, right? Make sense, right? So in case this guy is unreliable for small, right?
Oh, what is it called? Like O? What does it mean?
Little o.
Yeah.
Oh, little o. Yeah. So a function is a little o. So what if an is equal to 1 over n? It goes to 0 faster than 1 over root n, right?
Yeah.
That means it's a function of n which goes to 0 faster than 1 over root n. So it's going to be smaller compared to this thing.
Okay.
So these are standard notation if you take algorithm class. So you will see little o, big theta, and those kind of things.
Okay.
Yeah. So basically an over this thing, 1 over root n goes to 0 as n goes to infinity. Okay. Yeah. You have seen this in 760, little o chunk, right? Alright, so this is not too bad, right? This is pretty easy, okay, to approach. Another way to provide an estimation of the simulation budget is to use the so-called Markov inequality. Alright, so this is the fundamental result in 760, which we omitted this year. We didn't talk about this inequality. But let me just explain what it is. Markov inequality, consider a non-negative random variable and a constant which is also non-negative. Okay? Let's say we hope to estimate the probability x is greater than a. We have a bound of it. It's obviously, it's bounded by the mean of x divided by a. Why is that? Proof is very simple. Take a look at this equation. Inequality. A times indicator x greater than a is less than x in all situations. Right? First of all, let's try to convince ourselves that this inequality holds in whatever scenario. Okay, what can happen, right? Look at this inequality. If this condition is met, meaning x is greater than a, then this left hand side becomes a, and a is less than x, because this is the situation where this condition is met. If this condition is violated, left hand side is 0, so 0 is less than x, right? This holds no matter what. Right? Alright, taking expectation on both sides, right? We know expectation of indicator becomes probability, and the right hand side is ex, and we're good, we're here, right? So the probability is less than e over a. Of course, this inequality is somewhat crude. It may not, the equality may not hold. So if you're computing the number of sample size using this approach on this page, then it can be conservative. It can be just conservative, meaning you have a much bigger n in your analysis, though. But it provides a bound, right? Okay. All right. So this is not enough. Let's consider a derivative of this Markov inequality called the Chebyshev inequality. Okay. Now we no longer restrict our x to be non-negative. We consider x which is general. X can be negative, it can be not positive, doesn't matter. But we know it's mean, we know it's variance. Okay. The Chebyshev inequality is like this. The probability x deviates from its mean. By deviate, we include positive error and negative error, so we take absolute value. We don't care from which side. The deviation is greater than epsilon. Is bounded by the right hand side, and the right hand side is an increasing function of the variability and a decreasing function of the error tolerance, which makes a lot of sense, right? If x is more variable, it's more likely for x to deviate from its mean by this amount. On the other hand, if this error is big, it's less likely, right? How do we prove this, right? You can simply invoke Markov inequality. X is not non-negative, but x minus mu squared is non-negative. So treating this as our y here, as our x here. See, Markov inequality, we restrict x to be non-negative. So the x we're going to use here is going to be the x here minus mu squared. So plug this into, and for here the A would be epsilon squared. So taking x to be this guy, this y, and taking A to be epsilon. That's this, right? That's this. That's our y greater than epsilon. So this, now we're in good shape because in this formula here, y is non-negative and epsilon squared is non-negative, and we're good. Invoking this guy, we have expectation of the y over this guy, epsilon squared. But Ey is what, right? What is y? Y is this. E of this guy is just the variance of x, right? It's how we define variance in the first place. Okay. So the proof of Chebyshev is just an application of Markov. Very simple, very interesting, right? Okay. So how do we make use of this, right? We're returning the common interval problem, right? You're hoping to control this. You're regarding this epsilon as our absolute error, which we hope to control. We know that this is bounded by this guy, and if we can estimate the variance, maybe we can use the upper limit to, you can make the upper limit less than our epsilon. I mean, less than the confidence level. So, what I mean is, you're hoping this, right? But you have a control. You have a bound of it. So work on this bound. I don't know. Is this bound? I mean, see, this is greater. This is less, right? So if we put it into the format of this one, then this is going to be greater than equal to. This guy is greater than equal to, right? So we can let this one to be less than, to be greater than the right hand side, right? So it's lower bounded by something. If we let the lower bound to be greater than that right hand side, we're good. But again, we're overly conservative, right? We may be overdoing it, but at least there's a way to quantify this. So this guy is approximated by the sample variance divided by n times epsilon squared. The n comes out of this bar, and letting this be greater than 1 minus alpha, right? Less than alpha, right? Less than alpha. So run a pilot simulation with a reasonable n prime to estimate the variance. Then you got it. Letting this guy, treating this s squared as a given parameter, let this guy to be less than alpha, and alpha is given by this formula very easily. You can see that this formula is very different from the previous formula. Right? This is the n epsilon alpha that is said to be sample variance divided by alpha epsilon squared, which is quite different from this. I guess the way to use alpha is different, right? See, alpha appeared either in the denominator or in a decreasing function in terms of the more quantile, right? Of course, this is more, in general, this is sort of closer, and this is sort of more crude. You could also consider the alternative way using this sequential stopping, because this thing less than alpha involves n here and here, so there's two spots involving n, and this term involves random sampling to estimate. Okay. Let's talk about relative error. What if you're hoping to compute the required number of samples n gamma alpha such that the deviation from your estimator to the true value divided by the true value is less than a percentage. Let's say gamma is 5%. So instead of saying, oh, this absolute deviation is less than an absolute, let's say the relative deviation based on, with the base of the true value is less than a percentage. This is often considered in practice. Okay. All right. So this gamma, of course, is going to be a fractional number, right? 5%, 10%, 20%. So now, because we use gamma instead of epsilon, so our n will be a function of alpha and gamma, right? All right. A quick look at this objective seems to suggest that, okay, why don't I multiply, absolute value of mu on both sides, right? So I divide gamma here and there. Hold on 1 second. Let me see what I mean here. Is there a typo somewhere or no?
Yeah, I think it's multiplied by mu and then rearranged.
Yeah, so basically this is rearrangement of,
Yeah.
okay.
It's just mu.
Translate into an absolute. It looks like this can be translated into an absolute error. Because you can regard the multiplication of this guy and this guy as u epsilon. Except that you don't know mu. Because mu is something you wish to estimate. However, what if we replace this guy by the absolute value of our estimator, the best we have? Can we do that? And treat this as absolute. Right? Meaning, before we had this guy bounded by epsilon, which is given. Now we have this guy bounded by gamma times the best we can do to estimate epsilon, to estimate mu. Of course, when you have this kind of equation, I know n appears in this randomness, n appears in this random variable, and n appears here. You can still do your sequential stopping, or you can do your pattern simulation. We can make it happen. Basically, we have method to achieve this equality, to find the n sequentially or whatever. However, let's think again. Let's think again if this is good enough. Is it good enough to transform the relative error case to the absolute error case by simply doing this? Let's think again. Okay, take a look at here. This is what you want, right? You wanted this. If we do this approach, you're doing this, right? You're replacing the mu by x bar. So basically, you're trying to achieve this. Let's see. Moving everything to the multiplying this, then you get right hand side gamma times x bar. All right. Inside this absolute value, I subtract mu, I add mu. You can do that, right? Applying triangle inequality. All right. This guy is less than first term absolute value plus second term absolute value. So I have an a here, I have a b here, I have an absolute value of a plus b, right? It's less than absolute value of a plus absolute value of b. So I have upper bound for the right hand side. I keep the left hand side. Upper bound by right hand side, my probability gets bigger. Because it's more likely for this guy. I mean, this guy is less than a smaller number. It's less than the probability. This guy is less than a bigger number because it's more likely. So the probability gets bigger as well. I'm trying to explain this inequality here. Right? Make sense? Because this right hand side gets bigger, so it's more likely. Okay. Now I have this one. Why do I have this one? Because I want to move things around and combine with the left hand side. So I move this to the left hand side. I have a 1 minus gamma. Then I divide 1 minus gamma. And I divide mu. I have this one. Okay, let's compare with the original objective, right? You think you can do this, replacing the mu by, the best you have to estimate mu. The result is this, which is slightly different from the original problem. See, the right side is adjusted. That may not be good enough, because gamma is a fractional number, so this number is bigger than this number. So the n you computed based on this approach may not be large enough. Right? So if you find an n such that this is satisfied, is it guaranteed to satisfy this? No, because this is bigger. Because 1 minus gamma is less than 1, right? This right hand side is bigger than gamma in general. Of course, 1 gamma is very, very close to 1, you're fine. But in general, your simulation run is not enough. The sample, right? What can we do here? What's our solution? You see, this is obvious approach, replacing the mu by x bar. That's an issue here. You under-simulate. What can we do? That's the goal, right? Let's say this is, 10%. If you do this, you got 10% over 90%. I mean, 10 over 0.9, which is perhaps 11% or something.
Increase the value of n until we satisfy the first inequality.
No, but you know how to treat this, because you can treat this and this together as the epsilon. You can sort of do this, right? If you follow this approach, you're achieving this one.
Mm-hmm.
if you increase n, you still don't know how large it should be, because you don't really have, I mean, what I'm trying to say is that if you replace this guy by x bar, you're achieving this kind of inequality, and it's not good enough. If you, okay, of course you need to increase n, but to what, right? I need a correct number. Yeah.
Gamma over 1 minus gamma should be equal to the value.
You're saying gamma over 1 minus gamma, that should be the desired value. So let's say I want to achieve 10%. Let's forget about the gamma. Let's say this is 0.1. I'm going to make this 0.1, and I'm going to invert this function and solve for gamma. Gamma may be 0.9 or something, right? Right. Then use this prop. That's exactly what we're going to do. That's very nice. So we know, in general, we know this is not good enough because this is bigger. It's not good enough, right? This is because gamma over 1 minus gamma is greater than gamma. What you can do here is that, all right, for desired gamma, I'm going to look for a gamma hat such that is equal to this, and start with the gamma hat. All right? This is what you're going to achieve. So let's start with gamma. I want gamma to be equal to this guy, with this right hand side be gamma hat. Solving this equation, inverting the right hand side gives you gamma hat, a function of gamma. You can see that gamma hat is slightly smaller than gamma. I mean, it may not even be slightly smaller, right? So you should do what you do on the previous page using this smaller relative error. For example, gamma is 10%, perhaps gamma hat is 9%. So you should do that on the previous page, and you're fine. So this is basically an absolute error with adjusted parameter, and the adjustment is very easy to do. Make sense? It's pretty obvious. They're pretty nice here, right? So you have that, okay? Or solving this equation, kind of solving this equation.